Electrical Measurements and Instrumentation Lecture 3. In the last two lectures, we discussed about classifications and essential tasks required for measuring instrument. So in that we seen deflecting torque, controlling torque and damping torque, and how to produce the deflecting torque, controlling torque and damping torque. In this lecture, we are going to discuss why the scale is uniform in spring control and not uniform in gravity control. In controlling torque, there are two methods to produce controlling torque. One is spring control, second one is gravity control. In spring control, the scale is uniform, and gravity control, the scale is not uniform. And see why in this lecture. Actually, the function of the controlling system are it has to produce equal and opposite deflecting torque at the final steady position of the pointer. In order to make the deflection of the pointer, define it for a particular magnitude of the current. In the absence of a controlling system, the pointer will shoot beyond the final steady position for any magnitude of current, and thus the deflection will be indefinite. So without controlling torque, the pointer will move to the maximum value from the initial position. And the second function in the controlling system is it is to bring the moving system or the pointer back to zero when the force causing the instrument deflecting system or deflects is removed. So when the current is zero in the measuring instrument, the pointer will come back to initial position with the help of this controlling system. So in the absence of this controlling system, the pointer will not come back to zero when the current is removed. This controlling torque is usually provided by springs. Let's see the two types here, gravity control and spring control. Coming to the gravity control, if you see here, it is your pointer connected to your spindle. The point is at zero position. Two weights are connected perpendicular to each other. One is balance weight, second one is control weight, and all these points we discussed in the lecture 2 clearly. Now here in gravity control, a small weight is placed on an arm attached to the deflecting torque, right? Small weights. The position of this weight is adjustable. The weight produces a controlling torque due to gravity. The figure shown here is zero position and the controlling torque is zero. Let us assume that suppose the system deflects through an angle theta like this. Previously it is at here. I will show you one more diagram. It is controlling weight, right? Initially the point is here. Now because of the deflection, it is moving like this. Obviously the weight, control weight is moving like this. There is one force that is pulling downwards, that is gravitational force. It is in this direction. Because of this gravitational force, this arm having control weight moving in this direction. Moving in this direction. The direction is W sin theta. By using trigonometry, let us assume that from spindle to control weight, the length is L. If it is theta, it is also theta. If it is W is acting in this direction, obviously this is W sin theta and this is W cos theta. If it is W cos theta, it is also W cos theta. Side square plus side square is equal to hypotenuse square. This force is W sin theta in this direction. And the controlling torque TC is equals to force into radius. The force is W sin theta and the radius here it is from here to here, the length is L. So this is the force W sin theta, this is the length L. Force into radius, nothing but torque, force into radius. So that is equals to WA sin theta. Let us assume that these two are constants. Once it is fixed, the weight and also the length is constants, kg into sin theta, where kg is the constant. So that's why TC is proportional to sin theta. So whenever you change in the values in sin 30, sin 90, say whatever, the scale is not uniform, it is a cramped scale. So thus the controlling torque is proportional to the sine of the angle of the deflection of the moving system. Controlling torque TC is proportional to sin theta. The controlling torque can be varied by simply adjusting the positions of a control weight upon the arm which carries it. It is obvious that the instrument employing gravity control must be used in a vertical position in order that the control may be up. The instruments must be mounted in level position, otherwise there will be very serious errors. For these reasons, the gravity control is not suited for indicating instruments in general and portable instruments in particular. The system is normally not used now, except in cases where cost and simplicity is the primary consideration. Coming to the spring control, we know that in lecture 2 we clearly discussed about the spring control. Let's see here again. A head spring attached to the moving system shown in figure creates a controlling torque. And this is one spring, this is one more spring. It creates controlling torque. The essential requirements for instrument springs are non-magnetic, free from mechanical fatigue. Where the springs are used to lead current in the moving system, they should have a small sufficient to carry the current without temperature rise affecting their constant. They should also have a low resistance temperature coefficient. And the number of non-magnetic materials like silicon, bronze, hard rolled silver or copper platinum silver, platinum iridium, and the German silver have been used but have not been found satisfactory owing to some reasons or the other. For most of the applications, prosperous bronze has been found to be the most suitable material except in instruments of lower resistance like millivoltmeters. In this case, some special bronze alloys having low resistance may be used with some sacrifice in mechanical quality. Flat spiral springs are shown in figure below are used in almost all indicating instruments as the space required by these instruments is less than for other types. See here the practical one. These are the spiral springs. Thickness of the spring is T and width is B. One form of controlling spring is shown in figure. The inner end of the spring is attached to this spindle and the outer end carries a spigot which engages in a circular disc surrounded the jewel screw. The disc carries an arm which is slotted and displayed at the end. Displayed at the end means the width is going to decrease. The purpose of slotted extension arms is to allow the spring to be coiled or uncoiled slightly so that the pointer may be set at 0. The slotted arm is actuated by a set screw mounted at the front of the instrument and therefore 0 setting of the instrument can be done without moving the cover. So in the measuring instrument we have screw on the top of the instrument. By adjusting the screw we can make the 0 setting. By making the number of turns large, the deformation per unit length is kept small on full scale deflection. The controlling torque is thus made proportional to the angle of deflection of the deflecting system. For a flat spiral spring, the controlling torque developed by the deflection is Tc is equals to EB T cube into theta by 12 into L, where E is equals to Young's modulus of spring material, Newton per meter square. V is the width of spring, T is the thickness of the spring, L is the length of the spring, and theta is the angular deflection. So where E, B, T and L are constants for a particular spring. So now if all these constants, finally Tc is equal to K theta, where K is EB T cube by 12 into L, Newton meter per radian. That's a constant called spring constant or control constant, torsional constant or restoring constant. So finally we conclude that deflecting torque is proportional to the current flowing through the measuring instrument. Controlling torque is proportional to the theta in spring control. It is proportional to the sin theta in the gravity control. Coming to the damping torque, it is proportional to the velocity of the moving system. At steady state, the controlling torque is equals to deflecting torque. Now, then controlling torque is proportional to theta, then theta is proportional to the current flowing through the measuring instrument. So when the pointer deflects at an angle theta, it shows the current flowing through the measuring instrument. So that is in spring control. Coming to the gravity control, sin theta is proportional to I, then theta is proportional to sin inverse of I. So finally deflection is proportional to the current flowing through the meter. Once you observe the deflection, we can measure the current flowing through the instrument by proper scaling. Thank you.